Hello, everyone, and welcome to this week's Tech Tuesday episode. This is Horticultural Lighting Solutions, illuminating a path toward season extension. I'm Danny Zwischenberger, the Special Projects Coordinator for the Kentucky Horticulture Council. If you are new to our Tech Tuesday series, I encourage you to, after this presentation, go back and check out some of the content that we've already put out, including a few infographics on integrated pest management in greenhouses and high tunnels, a couple of excellent webinars, and most recently, a special feature on West Kentucky aquaponics out in Benton, Kentucky, where we go on a full tour of an incredible family-owned and operated facility and get to hear some of the many benefits of controlled environment production, as well as the challenges that they face on a daily basis. It's a super informative glimpse into what it takes to build and maintain an aquaponics operation. And Tammy and her family are dedicated to sharing their hard-earned knowledge with other folks who are interested in doing aquaponics themselves. So be sure to check it out. They touch on lighting systems, irrigation, nutrient management, greenhouse sensors, solar energy, really just a little bit of everything that we plan to deep dive into throughout this Tech Tuesday series. So we were really grateful to them for making the time to show us around. You can find that video and all of our Tech Tuesday content on the Hort Council's social media pages, and I will be sending out a follow-up email with links to our Facebook and YouTube channel so that you can get caught up. Just a couple of logistical notes before we get started today. A little disclaimer that throughout our Tech Tuesday series, we are showcasing a wide variety of tech companies, brands, and products, but the Kentucky Horticulture Council does not necessarily endorse any one of them specifically. The main focus of this series is to educate and empower growers, and growers should make purchasing decisions based on the needs of their own operations. And lastly, if you have any questions for our speakers today during this presentation, feel free to drop those questions in the chat, or if you prefer, you can just unmute yourself after the two speakers and ask aloud during the Q&A. So we'll go ahead and get into today's talk because I am super excited for this one. Our first speaker will be Arundathi Sharma, who is the Extension Associate for Greenhouse and Controlled Environments at the University of Kentucky, and brings with her a Bachelor of Science in Mechanical Engineering. She previously worked at InFarm, which is a vertical farming company in Germany, where she designed their lighting systems. Also with us today is Colin Brice, who is a plant specialist for the Philips Horticulture LED lighting team. Colin is a horticultural scientist and systems engineer with experience in greenhouse management, LED photomorphogenesis research, hard to say, and electronics design. Colin has a Bachelor of Science in Plant Sciences and a Master of Science in Biosystems Technology. And his graduate thesis focused on indoor cultivation of leafy greens, LED lighting systems, fluid handling systems, and electrical efficiency evaluations. So I'm thrilled that these two agreed to do this joint presentation for us today, because I think between the two of them, there probably isn't a horticultural lighting question that they can't answer, but no pressure at all. So without further ado, I will go ahead and stop sharing my screen, and I will let you take it away, Arundathi.
Thanks a lot, Danny. Let me see if I can get this set up properly. Okay, can you all see my screen there?
Yes.
All right, thank you. Well, first of all, thanks a lot for that intro, Danny. My name is Arundathi. Again, I work at UK Extension here in Lexington. I work with growers statewide and help them both with technical questions concerning greenhouses and controlled environments, but also in developing resources and decision-making guides that I hope will help people through the process of introducing technology into their operations. As mentioned, I previously worked at a company called InFarm, and that being a vertical farming company, the kinds of lighting systems that I worked on were what's called sole source. So we didn't have any input from the sun. And as such, there was a big emphasis on efficiency. And I had the privilege of working both with plant experts who had, interests in exploring, different dimensions of the relationship between lighting and plants, but also with, companies like Colin's that actually offer lighting solutions. So my hope today for this talk is to basically cover some very basic things that I hope will help growers go into conversations with these lighting design companies that bring their expertise with the right questions, the right set of vocabulary, and knowing what information to bring to those conversations. So we'll start with what we know, which is the sun. Most of the growers in our state are very much making use of free energy from the sun. And we all know very well that the drawback there, of course, is that the sun can't really be controlled. In the winter months, of course, we have fewer daylight hours. And here in Kentucky, you can see we lie somewhere between these two lines. These images are from an extension publication from Purdue. And so at the shortest time of the year, shortest days of the year, we're getting somewhere between 10 to 15 hours, depending on where you are in the state. And we'll get into some more vocabulary later on about how we might talk about quantifying that exactly. But the point there being is that as the season shifts, as the days get shorter, as the weather gets colder, your crops are going to be limited by different factors, whether that's temperature, water, or as we're going to be focusing on in this case today, lighting. And I think very often lighting is sort of the last thing that growers will come to as the thing they need to control as they try to grow their crops in the colder months. So why would you want to introduce supplemental lighting? Well, there's a few reasons, and you'll see some terms on this slide that we'll get into some more detail later on, but one of those reasons might be that you actually want to grow crops that don't usually grow here at all. So you want to have something tropical that needs tons and tons of light. Then your goal is actually to increase your light intensity. And that's something that we measure in a unit called photosynthetic photon flux density, which is a very long way of saying light intensity. It's, in other words, the rate at which a number of light particles pass through a square meter every second. The other thing you might want to do is actually just extend your day, which alludes back to what I mentioned in the previous slide as far as number of daylight hours. And that's something we call photoperiod, or number of light hours that the plants see. And that might be something you'd want to control if you're trying to grow something that perhaps does belong in our climate here, but maybe you want to grow it out of season or in an extended season. So a good example of this is you're trying to get your tomatoes to market a bit earlier than everybody else, or even produce them in the winter months. And that number of daylight hours combined with light intensity is something that we call daily light integral. And then finally, the last reason you might want to include supplemental lighting is actually to do some careful things around manipulating plant response and physiology. And this can be influenced by basically the color of light that you're giving your plants, or the spectrum. And you'll see this in some operations where they want to prevent or induce flowering in certain crops so that they can have them at market at a very specific time. So yeah, a good example of that is, chrysanthemums, where you want them to be ready for sale at a particular time. So when you develop a lighting design, there are some key parameters you want to keep in mind. And this is where you want to actually have targets when you are thinking about these calculations of whether it's going to be economical or appropriate for you to introduce lighting into a growing system where you don't already have it. So one of these parameters is quality, and we measure this using the light spectrum, or what different colors of the light are represented. So in the figure that you see there, you'll see a bunch of different spectrums. They mean different things. So you'll see on the top right there, if I would have a blue LED and a red LED, that's what that spectrum output would look like. I don't want to go too much into detail there because I think that'll actually be a topic that may come up later. But what I mostly want to point out here is that plot that you see in the bottom left there. So when you go out onto Amazon or wherever and you look at what different lighting products are out there, they're going to throw a lot of different units at you about how to understand the quality of light that you're receiving, the quality and the amount of light that you're receiving. One unit that you'll see used a lot is something called lux. And this unit is actually not really appropriate for when we're talking about plants, because as you'll see there, that's the spectrum of human sensitivity to light. The plot above it is the absorption from chlorophyll. And as you can see, these plots are kind of not at all the same. You know, what our eye does is really plays up green light, and plants actually tend to absorb much more of red and blue light. So again, that will probably be addressed later in our discussion today, but I want to point that out to you because really the units that you want to be interested in when you look at a lighting product and you want to understand how much light it's outputting is going to be something that looks like this underlying parameter here, either of these, whether that's power per area or number of photons per area. Finally, uniformity can also have an impact on your light use efficiency. Again, something to get into a little bit later. And all these things put together, you know, finally, the way that you actually use your lights is going to be controlled by how long you have them on and off, or your photo period. The important thing I want to mention here finally is that it is really important for you to understand what conditions you're dealing with before you go ahead and decide what design parameters, what your design parameters are quantitatively. If you know that you have a tunnel that experiences a lot of shade, you probably are going to need more supplemental lighting. So that's what I want to emphasize there, is that, yeah, you need to know what you have before you can figure out what you need to add. So what products are commonly available? Here again, I'm not going to go into too much detail because we'll hear quite a bit later on about LEDs specifically, but just what I've kind of seen around. Of course, some folks will just sort of put in a classical light bulb, as you see in the diagram there on the right, but of course, that's not terribly efficient, and it's also, I think, diminishing in popularity. What you see a lot more of is LEDs or HID or sodium lamps. And what I've seen some growers doing is actually using those sodium lamps in the shoulder seasons where they maybe don't yet want to turn on the heat. They're gas heating or wood heating, whatever they're using, and instead actually use the fact that a sodium lamp is not very efficient to their benefit and use that heat from the lamp itself to heat up the greenhouse while also adding some light into the system. One thing to consider there, of course, as well, is that when you cycle lights like that, so any kind of fluorescent type of light, or a sodium lamp, you're actually reducing its lifetime. So it's not the sort of light that you want to be flipping on and off all the time, but rather one that you would keep on for some time and then turn off. And then of course, LEDs, you see all kinds of products on the market. My general advice to folks is it's generally better to go for a higher quality product. I'm sure Colin will have something to say about that later. So I won't go into too much detail there, but again, the one of the big benefits as well with LEDs is that you do have control over the light quality or the spectrum. So if you are kind of trying to induce a particular reaction in your plants, then you probably want to go down that path. And of course, that they make much more efficient light output. That was actually not the case some years ago, and increasingly, it is becoming more and more economical to opt for LEDs. So finally, I want to just wrap up with a broad overview of what these development steps are if you're thinking about introducing supplemental or artificial lighting into your greenhouse operation. First of all, you need to know what your requirements are. And that ultimately really comes down to knowing your own business plan. How much are you trying to increase your yield? How much longer do you want to extend your season? Where are you going to sell this product? These are questions you need to answer before you start making investments in technology, because it doesn't just cost money to get this equipment, it costs money to operate it, and you need to know that you're going to actually be able to pay it off. So that's the first point that I really want. If you take nothing else from what I've said today, come home with that. You want to have at least some kind of target for how much more money you want to be making as a result of introducing this feature. And the second thing you want to do is actually, based on those goals, decide what kind of light is going to be most appropriate for you. And that's what's going to allow you to estimate what your operating costs for this product are going to be. And that's how you'll know what your profit margin should be or what you expect it to be. And then you start getting into the stages where it actually might make sense to depend on more expertise, technical expertise, or outside help, where you want to strike a good balance between having good light uniformity in your growing system, while also not necessarily inflating your upfront costs too much. And that is that's where, a lighting designer can be of a lot of help to help you figure out the layout, the number of lights. And then finally, it's up to you how you use those lights. Use them efficiently, understand your system, know how much light you have already in your system, and understand the relationship between your use of those lights and what it does to your crop. So to sum that up, yeah, is it worthwhile to invest in lighting? That's going to depend. So I'm going to close with that. Once again, if any of you is interested in growing indoors, if you have questions about introducing supplemental lighting into your operation, we're here to help at Extension. Feel free to reach out. My contact information is here.
Thank you, Arundathi. I have a few questions, but I'm going to hold them till after Colin speaks.
Sure, yeah.
So if you want to stop sharing your screen and Colin can hop on.
All right. Yeah, great talk, Arundathi. I especially really like the point you made showing the kind of inverse relationship of the human eye visibility and the photosynthetic absorption curve. I think that's one of the more fascinating kind of design features of this whole space we work in, where humans and plants have kind of co-evolved, and I think that point really illustrates that. And I'm sharing. Can you see my screen?
Yes.
All right. Well, yeah, thank you for having me today. My name is Colin. I'm excited to be here. And I'll focus a little bit more on some of the practical applied side, as far as taking you through some of the need to know features on a light design and what we call a light recipe, and kind of build upon some of the concepts that Arundathi touched on, and then finally take us through somewhat of a template example when it comes to working in specifically around a project, a hypothetical project in Lexington, Kentucky. So my name is Colin, and early on I started working in LED horticulture applications at the University of Tennessee. So I've really been focused on this field of application science and agronomy since around 2015. Started working in that long word that Danny mentioned, photomorphogenesis research. And once I realized that was the field I was working in, I'm like, all right, I'm in a rabbit hole of technical application, and I just kind of rode that as far as I could. So I've really been focused on LED work and assisting growers in adopting, optimizing, and designing their lighting application systems, as well as supporting them on kind of an internal, on the Philips team as an agronomy consultant. So we really pride ourselves on bringing that scientific integrity to the table, and it was a really great opportunity to kind of set forth into the big world of commercial, large-scale agriculture out of school. So it's been a pleasure working in this field so far, and hopefully can bring some of what I've learned and what our teams have learned along the way to the group here today. So I wanted to focus on these three kind of key areas for the talk, and first go through just a bit of an overview of specifically pertaining to LEDs, the idea of why supplemental lighting is important in kind of a broad stroke, and then switch over towards a little bit more detail around horticultural light recipes. So what does that comprise of? What are some additional concepts to kind of build on some of those ones that Arundathi already touched on? And then finally going through some of the overview of our approach in working in different crop applications that are specific to those crops, so that you have an idea of what are kind of the general ranges and boundaries of light intensity, photo period, and hours, and so forth, so that you can kind of have some of that information in your back pocket to move forward with. So first, just jumping into kind of an overview on LED supplemental lighting. This diagram here, I think we've maybe seen it in so many different forms, but I like to show it, and I like to use it to illustrate the fact that while photosynthesis being the primary driver of plant growth depends on all these factors in the equation, like carbon dioxide, water, glucose, and oxygen being the outputs of that equation, that the light available to that plant is one of the primary drivers of that process. And Arundathi touched on this, and I think it's an elegant point. When you're in the greenhouse and you have all the first things you work to control most of the time are these other secondary factors of growth, like CO2, temperature, humidity, having an irrigation protocol that delivers the right nutrients to the plants, or having a healthy soil base if you're in natural soils. So most of the time, those are more of the low-hanging fruit to optimize and put within a range that can accelerate plant growth, whether off-season or during a typical growing season. But at the point where light starts to become a diminishing factor, we see that increasing the light available to the plant allows the most optimization and improvement of either yield response as well as secondary quality. If we look at some of the signaling responses we see in plants that can induce flowering, induce better branching if we're talking about a floriculture crop, or also optimize the rooting speed of, let's say, an unrooted cutting. And just to kind of simply illustrate this, this is kind of a graphic that we put together of if we're in the greenhouse and we're supplementing light, we're taking what available sunlight exists at a given point of the year, and we're supplementing to the amount that's needed to optimize growth for that grower's desired outcomes. And then, of course, if we look at sole source lighting and move indoors, which there's more and more use cases popping up in the market where we see growers using LED lights for the most part in these conditions for the 100% of the light provided to the plants. And just to briefly note, some of those newer application fields we're seeing is, of course, the container farms, where we're seeing, I think we saw a question in the chat mentioning one, where you have full control and consistent production year round, and you're controlling every variable of production within the indoor sphere. But also we're seeing that greenhouse operators are moving towards more sole source applications for, let's say, their young plant production areas, where they want to have more of a limited investment on the higher input cost for sole source lighting and full controlled indoor production, but they're utilizing that to their advantage to create complete control and uniform production and maximal quality for their for their young plants, because they get a bit more, you get more bang for your buck in that sense. So just to kind of take a sweeping overview, view of what we see in this market, typically what we're seeing in greenhouse lighting, which predominates most of the lighting application field that we work in, we see hybrid with HPS lights and LEDs, where you see photographed here on the top. And that's where growers are still using, usually about half the fixtures will be HPS, and then the other half will be LED, and we'll often see those on a checkerboard design. And then, of course, we still see full high pressure sodium lighting systems and full LED systems like we see pictured on the bottom right. A lot of reasons to consider the different solutions. I know that, generally speaking, that high pressure sodium lamps are less expensive on the front end. And like Arundathi pointed out, they generate a lot of heat initially. And with full LED systems, the upfront cost can be higher, but the product reliability, control over the spectrum, and the fact that you have a 10-year lifespan on a product that doesn't need to be replaced, versus with HPS, typically 10% of the light output degrades over 10,000 working hours. So within a few years, we're constantly replacing bulbs. And with an LED, we see about a 5 to 10% reduction over 36,000 working hours. So that's typically over 8 to 10 years of use, depending on how many hours are used in a year. But the operating expense of an LED, if we have the light levels the same, we see about half the energy use in an LED with an efficient spectrum. And then if we look over towards the heat from an HPS, it's often more cost effective to bring that heat back into the greenhouse through natural gas scenarios. So every time we approach a situation, we do see, this checklist of our natural gas prices and your boiler systems able to make use of increased usage, so that we can actually result in that same heat input to the system, because there are important considerations when looking between these solutions. And we want to make sure that operators have every bit of associated impacts to their operation accounted for ahead of time, so that we can make sure that they can take advantage of the efficiency gains that they can make with LEDs. But looking at the overall kind of seasonal approach, I wanted to touch on the fact that when we look at summer versus winter, our light levels and associated total sums of light. I know Arundathi pointed out DLI, and I just wanted to kind of reiterate that unit as there's a lot you can unpack in the definition of a daily quantity of PAR photons, so photosynthetically active photons. We capture and measure those on a square meter per day basis, but really what's crucial to know, the important part of the daily light integral, is it's the total sum of light we achieve per day over a surface area of a square meter. And when we look at the summer versus the winter, and we feel it, we see it when we get into the winter months, the amount of light that's available to that crop is much lower. So here's an example published through Clemson University, where if we look at Kentucky, we can see November, December through February that we're really in the lower end of the scale range here at between 10 moles to 20 moles outdoor. And we have to keep in mind that that's not what's actually hitting the crop. But this winter season is when we see the largest use of supplemental lighting systems. And that's because, as this figure here illustrates, is when we look at plant growth, we want to achieve an amount of growth that optimizes the potential that's there, but not exceed an amount of input cost that you eventually don't achieve a growth response from the plant. So we're always trying to target this in the off season or the low light season, a light intensity and usage strategy that achieves this kind of sweet spot as designated here, that we've taken advantage of all the linear gains that we can make in the system to achieve a goal, and we're not increasing our dollar input to that space where we're not receiving the same output as far as plant productivity. And just a couple things to note as far as the losses. When we look at the greenhouse, the outdoor radiation levels, like shown on that 2 slides before, can be 10 to 15 moles per day. but we're usually losing 30 to 40% of that through the glazing material itself. And if you're in a glass greenhouse, usually you lose 30%. And if you're in a double wall poly house, usually you're losing 40%. So the material being used has a large impact. Where you're located in the country certainly has a profound impact on how much light you can expect to receive. Usually when you move north, you start to have lower winter light sums in the greenhouse. But as we saw, even in Kentucky, when we get into the winter, there's still a pronounced effect where often, as we'll see later, it's below the optimal threshold of light to grow a high quality plant and a high productivity crop especially. Some other factors just to briefly touch on: the structure, the design, how the posts and trellises are laid out. The cleanliness and age of that greenhouse makes a large impact. So if we have a poly house that hasn't been cleaned or had the panels replaced in many years, that can often reduce those levels much further. As well, the weather conditions, so how much expected cloud cover an area gets plays a large role. I know here in the Appalachia region that on a latitude for latitude basis, surprisingly, we actually have less light in some of the winter months than if you look at a corresponding almost a Mediterranean or Baja kind of climate in like in California. And it's just due to how much water we have moving through our watershed and our environment here. We often have a more pronounced impact of cloud cover. And then lastly, obstructions and local shading factors like hanging baskets, and especially when you have hanging baskets like shown here, can play another large role in terms of the light loss to that overall system. So all of these things combined kind of bring us into light recipes and how we associate the needs of a system in terms of hitting that goal. What are the things we're actually accounting for? What's that kind of game plan and strategy that we're coming up with to start working on from the outside in? You know, what do we have? What are the factors of an individual site? What are the crop needs? And how do we control the design factors so that we achieve the needed results for an operation? And slightly different terms, but some of the same concepts that Arundathi presented. So I don't want to spend too much time going in depth on each one, but just to reiterate that the light level or light intensity we measure in micromoles per square meter per second. If you're not working in this unit for horticultural applications, or if a lighting provider is not leading the conversation around this type of quantity of light or light intensity unit, then be aware, you know, that's how we're standardizing the amount of light towards horticultural applications. So it's really important that we're working in that unit and that we're basically looking at the amount of light on a photosynthetic response basis. So that's an important one to keep in mind. And then for spectrum, generally you'll see a lot of, it's one of the more interesting and fascinating topics of discussion. There's a lot of focus on it in the industry, but generally speaking, we see a lot of high red content in horticultural lighting spectra, sometimes with a pinkish or reddish hue to the lights. And then alternatively, we see a lot of white lights, so broad spectrum white lights. Our philosophy is that of efficiency and driving down operating expenses wherever possible with achieving the needed results. And there we see that having a high red content, which I'll touch on a little bit later, increases the efficiency of the system on a photosynthetic response and electrical input cost basis. But you can go all day on spectrum, but I won't spend too long later on going in depth. And then uniformity, that's the third part of a light recipe that we call the uniformity of light levels. So how much do the light levels vary across the crop surface, which is important to ensure a uniform growth response to those crops, as well as the positioning of the light. So if we look at a high wire tomato crop like shown here, or a cucumber crop, how are we putting lights into the canopy? So there's a lot more opportunity to kind of customize form factor and application with LEDs that kind of lend to that point. And then duration. So how long are we running the lights? How many hours are we applying light at full load? Or if we're dimming, how are we controlling that system on a time basis that with the combination of light level and duration will give us our daily light integral or our daily light sum per day. So as far for light level, just again, this is measured in micromoles per square meter per second. And another important point to make here is that it's a function of the total fixture output. So that's what we call our photosynthetic photon flux, or PPF. That's what you'll see in a manufacturer's spec sheet. And that's in micromoles per second. So that's how much light an individual fixture is putting out, how many fixtures are in an area, and how is that light being dispersed to that whole area. So these three factors really interact in the grow space to arrive at what is the amount of light, or the intensity of light that we're actually getting at the crop canopy. And I think an easy way to look at this is that PPF, that kind of official spec sheet term we'll see, is on the fixture level. So what's the output of the fixture in terms of photosynthetically active photons or particles of light? And then PPFD, it's the same unit, just with the word density applied to it. So it's photosynthetic photon flux density, which that's at the crop level. And that's the actual final density of light transfer that we're getting to a growing surface. So those for me are kind of easy ways to remember it. And when going into discussions around lighting systems, to make sure that we're looking kind of apples to apples between different products, making sure that we understand the associated impacts of a lighting design and so forth. So switching gears a little bit over to spectrum, I wanted to show this slide here, and I think it really illustrates a really important point. And if we look at the efficiency of a luminaire or of a light fixture, we express that efficiency in what we call micromoles per joule. So that's how much light, how many particles of light we're getting per joule of energy. And that unit is dependent on not only the fixture design and quality, but the actual optical efficiency of a given color of light and how many photons are produced given an amount of input energy. So it's a combination of the optical power of that wavelength and then the electrical power needed to generate a certain number or particle of photons of light. And what we see is that blue light, and we know this with UV, it's very high energy. So that's why when we go out in the sun, we have to kind of take care of the UV that we absorb. It's that high energy light can cause damage to cells, but it also, on a per photon basis, we have more energy. So red light, inversely, as we move towards infrared and like towards the red side of the photosynthetic color range and spectrum, we're able to generate more photons of light as we move towards red. And this is designated with 1 watt of power on the amount of photons. And we see, if we look at the micromole per joule ratings, or basically your output efficiency by color, we see that red is the highest on the amount of photons we can get per input energy, and that green and white are kind of on the lower end of the efficiency ranges. What we see from, and I don't have one on the slide here, but I think the McCree curve is a good way of illustrating that. And Arundathi showed in her slides that the photosynthetic response range is really targeted in that blue and red region. But generally speaking, we see that a number of photons, a quantity of light, is really the needed, the more dependent variable of how much growth response we're getting. We see a very similar growth response for a given quantity of photons across that whole, what we call the photosynthetically active range. So 400 to 700 nanometers, that's all the way from blue all the way up to a deep red color, kind of shown here on this graph, all the way from blue spanning all the way to red. So if we can achieve the same growth response with a given amount of light, and we can design lighting packages to provide that light in ways that maximize the electrical efficiency of the application, then we want to do that as manufacturers. So generally speaking, as far as designing horticultural spectra, we look at deep red as a way to maximize efficacy and become more efficient on a photosynthetic basis. And as well, we look at adding blue, green, and far red only as much as is needed so that we elicit different outcomes in the crop. So for blue, to make sure we have the right compactness in the crop, get the right physiological response as far as the crop's architecture. And there's also some other reasons to add blue, like getting better coloration out of red lettuces. But not to go too in depth, we use blue to get the right crop quality and make sure it's in the right amount to achieve that. And then for green, as Arundathi pointed out, that the green is really, human eyes are very sensitive to that color range. So adding enough green or white light into a horticultural light will allow a proper color rendering and human viewing experience of that crop. So for integrated pest management or nutrient control, it's nice to have usually around 5% in a spectrum so that you're not sacrificing your efficiency too much, but you're getting the needed viewing ability out of that surface of the crop. So as a guiding principle, we try to use as much red as possible and add blue, green, and far red only as are needed. Switching gears again to uniformity, and I don't have too much to say on uniformity, but I did want to show a graphic here that illustrates how important a light design, a proper light design is, and not just doing kind of back of envelope calculations on this, but using knowledge about how many lights I should roughly expect to have to start on a design is a great starting point. And when you have a simulation software to design an actual light recipe or light design or a light plan, working with a team that can provide that and make sure that you have good uniformities in your grow environment is really important. So what you see here on the left is what we would consider a good uniformity situation of over 80%. And we look at uniformity as the average light level divided by your maximum light level. And that's a good indicator within the crop area of how much that light varies over the cropping surface. And anything below 70, we would really try to stay away from, as you would see a pretty inconsistent growth response to that crop. So lastly, on duration. So here we're kind of getting into more of the meat of what I wanted to show. And here is just a general working guideline that I put together for different crop types, where first we work backwards when we look at lighting designs and applications, is how many hours of light can we apply per day? Because that gives us a starting point on what intensity would be needed to hit the total amount of light or the daily light integral that we're trying to provide in a given part of the year. So, and I'm happy to send these slides out if this is helpful, but feel free to screen grab it. But this is kind of our general working advice that for different crop types like herbs, lettuce, and ornamentals, especially within ornamentals, we see a wide range based on the photoperiod response in terms of flowering. But for herbs and leafy greens, we're generally working between either 18 and 20 hours or 15 and 20 hours. And then for tomatoes and cucumbers, we see kind of a commercial standard lighting hours and day length of 18 hours. And then, of course, if we see, as we work some out west in cannabis applications, that the photoperiod response of these two crops is different, whether we're wanting to grow a vegetative plant or a flowering plant. So diving a bit more into the crop-specific applications, just have a couple more slides to go through. And so this is our working advice for daily light integral across most of the crop segments that we work in. What we can see from this is that with ornamentals, you could be working with a shade-loving tropical, a highlight-loving tropical, or chrysanthemums, lisianthus, so many different species that have so many different needs. So this really important to look at it on an independent variable of the species being grown and what are the light hour requirements of that crop to get the needed flowering response, and then work backwards from there. And then for herbs, we see quite a range. If we look at basil towards the high end, and then herbs like cilantro and dill being towards the lower end. And then lettuce, we see kind of a tighter range. Actually, we're seeing the ceiling on the lettuce light sums kind of go up and up as growers work with more high light tolerant varieties to maximize their productivity in the greenhouse. So about 12 to 16 is a good range in terms of moles per square meter per day to achieve a good response in most lettuce varieties. And then for berries, we're going a bit higher, 18 to 24, and then cucumbers and tomatoes towards the highest end of this in the fruit and vegetable sphere, especially with going up to 25 or even 30 moles per day. And just for reference, like an outdoor sunny day in summer is about 45 to 50 moles. So we're not quite pushing these as hard as they get pushed in the outdoor conditions in summer, but we're still relatively much higher than some of the other crops. And then, of course, for cannabis, much higher light loving plant. I know there are some hemp operators in our markets, and I'm based in Nashville, so there's quite some activity going on in that sector as well to be aware of. And then quickly, just wanted to go through an example here for these different major crops that we work in. With the target DLI given, what would an intensity that you would see in terms of micromoles per square meter per second? What would you expect to see to achieve that in this case, Lexington? And then what's the associated light increase per year? So what's the total number of moles we get per year per square meter without lights? And then what's the increase from adding lights and deploying them to this target DLI? And what we can see is that for tomato and cucumbers, quite a lot more usage to hit that 25 moles. And we're increasing within the linear response range of photosynthesis. So really expecting to produce 32% more yield per year. So I think this is one of the big points that I do want to drive home, is that lighting can really increase the productivity in terms of a yearly yield of these crops. And this is just looking at the yearly total. So as you see for strawberry and lettuce, it gets a bit lower, but we're enabling production in periods of the year that otherwise we can't grow a high quality crop. So often there's not a lot of field product on the market to compete with. So the prices that growers can command is a bit higher. So that, 15%, 23%, or 8% isn't really telling the whole story as far as what can be made, what can be achieved on an operating revenue basis. And when we look at an example, so I took the example for tomato, and assuming we're in Lexington, Kentucky in a double wall poly greenhouse, what does the light conditions in the greenhouse on this gray dotted line look like without lights? So what's the natural solar daily light integral that we're getting? And then what's it look like when we deploy the lighting system at that 220 micromole intensity? And what we can see is we're nearly right at that 25 mole target for pretty much the entire year. We're a bit shy. We're not going to invest another 30% up front in lighting just to put this small amount of capacity onto the system. But this is kind of how we would design an application in this region. And then when we use the lights, how are we running them to achieve that outcome? So we're working backwards from that 18 hours per day and slowly reducing our hours as the daily light sums start to increase until we're not even really using the lights in terms of providing a growth response in these summer months here. And I just wanted to highlight one example, an actual case that we worked with, and that's Great Lakes Growers. So John Bonner, he's in near Cleveland, Ohio, and we've worked with one project in Kentucky so far, one of the at-harvest sites, but it's a new market as far as these applications. I think it's really growing, and so we're excited to support its growth and development. And there are some nearby projects like John Bonner's where we've worked for many years in helping him improve his lettuce and herb cultivation. And in this case, we worked with agronomics, and I just wanted to touch on that he's seen a significant increase in his winter production of 30% through the lit season, was able to reduce the tip burn that he experienced in the crop and improve coloration in the red varieties is kind of the take-home results that he found. And so I'll work with cultivators like this over many years, before they're installed and after they're installed, to assist in their lighting deployment strategy, and as well even get into more comparison strategies. I know in this case I've worked on comparing light levels and seeing the operating input efficiency when it comes to different parameters in the greenhouse. So we're always excited to set up partnerships like that and be able to see results where with our agronomic services teams we're really able to deploy that that application knowledge to make the projects a success. And so just to quickly summarize, we touched on a lot, and I know I moved pretty quickly. There's always so much I do want to cover in these talks, and there's always feels like there's not enough time to go through them, so I try to go a bit quickly. But just to recap, supplemental lighting is often a really important and necessary factor to enable off-season production, but also to maximize production on a given square meter per year. When we look at a light recipe, the important things to know is intensity in your lighting hours, which give you your total quantity of light, are really the prominent factors to growth. I know spectrum is often the most talked about, but it's really important as it comes to efficiency of that deployment strategy, and is actually a really secondary factor when it comes to the response of a crop in terms of growth, and often even in the secondary quality attributes. There's only so much that we can achieve with spectrum, especially as the amount of light from the artificial lighting system becomes less and less. So if we move further south, we're providing less relative to the total from the lights. So spectrum even plays a lesser role in regions like ours, whereas it plays a larger one in somewhere like Norway. The other thing to note is when we're working on a lighting application and we're trying to design and look at the benefits that can come from applying lights to a crop, is really make sure you're working with knowledgeable providers that are going to provide scientifically accurate information on all of these types of factors, and won't try to over install light intensities or push a spectrum just because it maximizes on a rebate. Really looking at what you need to succeed and providing honest information every step of the way is a crucial factor. And then lastly, in Kentucky, even though we do see a lot of light come relative to other places that are always using lights, like in Canada, there's more light in the winter, but lighting can still significantly improve the overall yield response on a yearly basis and enable off-season production where otherwise we wouldn't be able to, and capitalize on those higher prices. So it's, I think really the last thing to say is really it is important to look at an operation and say, what can I do? What can be achieved? And when it comes to lighting, if there's a benefit that you're leaving on the table, I mean, it's better to know that and be able to assess that from top to bottom. And that is what I have today. So thank you. And yeah, it's a pleasure to be here.
Thank you so much, Colin. That was
Sure.
incredibly informative. Luckily, this is being recorded, so if people do want to go back and get some of those tips for how long each crop needs, the daily light. I'm like struggling with all these terms. It's so much good information. So I'm definitely going to be going back and reviewing this. But I have a couple of questions that have come directly to me, and also one in the chat. If you all who are listening think of any as we go, feel free to just drop those in. Chelsea asked, have you seen any use of supplemental lighting for in-ground leafy greens production in high tunnels or other semi-controlled environments?
Want to take that, Colin, or I can?
Sure. I've seen one project in Michigan doing it, and we don't see a lot of it. I actually, I talked with my manager is one of the commercial leaders in North America, and we've always wanted to start a business on the side and do spinach and high tunnels and deploy our lights in that scenario. I think it's an interesting field that we don't see done much. And my only piece of advice there would be if you're not able to warm the ambient air temperature around the plants and you're adding supplemental light, it can be a challenge to make use of the added light. So if in any way possible, I don't know if you just like drop in your sidewalls or if there's any way to increase the root zone temperature. I mean, you could consider running heat pipes, burying heat pipes into the soil as a way to increase your heat with your light. That's kind of our general working advice when adding light. So it can be done. We don't see it done much, but there has been one case that we've seen.
Yeah, I can maybe add to this too. I mean, I've seen in ground production, I mean, in Kentucky, that can kind of already happen year round with leafy crops, at least, in combination with row covers. So that is what I've mostly seen folks doing to keep the crop protected from temperature swings. So I guess the main reason to introduce lighting in that situation is actually just to speed up the crop, would be my guess. Assuming that it's light limited in those stages and that's what's keeping it from actually growing faster. But yeah, I also have not really seen that among producers here so far.
And I think it would work well. I mean, I like your point of, well, and I was thinking at it from like the winter. Sometimes I have this tunnel vision around the winter production months because we see that being when the lights are used the most. But the shoulder seasons with the high tunnel, as long as you can achieve anywhere between, I would say 74 degrees Fahrenheit to 78, it's kind of what we would consider our working plant temperature to start applying light. So as you could easily achieve that, I think, as long as the sun's out in most of the state. So as long as you're able to kind of trap some extra heat, I do agree that it could be an advantage.
Awesome. Arundathi, you touched on the high pressure sodium lights. Can HPS lighting significantly supplement heating sources? And also another question kind of came in, do LED lights also give off a lot of heat that would impact temperature management?
Yeah, so I wouldn't recommend using a light source as a substitute for heat. I think Colin already touched on this, but yeah, certainly when it gets cold, you gotta have heat. And I see plenty of producers using a variety of different methods for that. Some of them have heated water that comes through. They have wood burning stoves. They have gas. There's all kinds out there, but no, I wouldn't recommend using that as a substitute. What I've seen is use of the lights, and again, more of the sort of shoulder seasons where you think you might have a bit of a colder day, and the crop is, I guess, adjusting slowly. But I mean, maybe Colin, do you want to address the LED efficiency a bit?
Sure. So if we're looking at it, say, just to have apples to apples, if we have like 1,000-watt fixture on the same number of fixtures in a given area, if we have HPS, and what we typically, at least in our teams, what we would recommend for most applications is like a highly efficient high red, but with enough white and blue. And we call it a deep red, white, low blue is what you see in like tomato and most of the crop applications. It's producing half the amount of heat and twice the amount of optical light energy, or like photosynthetically active light. And so it still produces, I mean, a significant amount of heat. So, I mean, HPS, I think, produces like 66% of the energy you put into it becomes heat in some form. And 34% on the LED becomes heat. So it's right about half. And it still does warm up an environment to an extent, but not nearly as much as an HPS does. And I didn't touch on this in the talk because you could talk almost all day on this one point, I think. But if you look at the amount of, like, how much it costs to provide an amount of heat through an electrical ballast using a general like 5 or 10 cent kilowatt hour rate versus the amount it costs to provide that same amount of heat through a natural gas system, it's usually 9 times more expensive to do it with electricity, as long as there's an average natural gas price available. So the question then becomes, well, do I have access to natural gas at a good rate? And can I bring that into the system? Because when you move away from HPS, you do lose heat, and you need to, those two need to be in balance. So making back that lost heat, while it has extra steps and considerations, it's so much more cost efficient that usually that's why we see growers moving towards LED. That's a long-winded answer.
Excellent. Mike says, not to be rude, but budget price for 20 by 100 with 10-foot high for tomato supplements. Just a ballpark to start thinking about planning. So for a smaller scale, like, what does that look like?
Well, luckily, Mike, we have some of the homework done on it because I got the light level that would be needed for Lexington. So I just got to do some quick envelope math real quick. So 20 by 100. So that's 2,000 square meters. And then if we divide by 10, 186. All right, I'll get back to you in a sec on that. It just take me a little bit of math.
In the meantime, what do you see as the primary barriers to entry on LED lighting systems for growers in this region? Is it electrical infrastructure on site, energy pricing, something else?
I think there's a couple of things to think about there. The first being, and I think we, in different ways, have kind of addressed this, Colin and I, in our respective talks, but lighting tends to be kind of the last thing that people look at, So, if I look at who is even trying to produce throughout the winter, I think for the most part, people are growing crops that they don't already need to, start adding infrastructure in order to produce. So, that's, as mentioned, leafy crops that you can actually pretty much cultivate through the winter months without any additional lighting. And the upfront costs associated, probably more so with LEDs than maybe other types of lighting, maybe put a lot of folks off of making that investment before they necessarily want to jump into, let's say, December tomatoes. So I believe it is perhaps to a large extent upfront costs, actually. And then also just knowing about where to sell this product, right? You can't jump into that investment if you don't know where you're going to sell the end product. So I think, making more public the availability of off-season markets, or even opening up those markets a bit more, could present a lot of big opportunities for growers.
Yeah, I would agree there. And another one that we maybe see more of it just from where we're kind of positioned in the market is, certainly startup cost is a big hurdle, but then we see a lot of like boiler capacity. You'll go into a greenhouse that has been working on the same boiler system for years and years, and maybe they've been using HPS for years and years, and everything's kind of dialed in so that they're already at max load on the boiler system. And if they go away from HPS, they'd have to renovate and put in a new boiler. And so that's another one. And then the electrical capacity we see a lot, where a lot of our partners sometimes that we work with will have to come and install, new power to the site, or increased power to make use of, especially if the grower's not using lights and wants to start using lights. That's when we see that.
Awesome. Alexis says, as an agent, I'm getting a lot more questions from people wanting to do lighting for tulips over winter, often in basement type place or a converted cooler. Do we have a fact sheet in CES I can pass along to them?
I do not have one on hand, but I'm going to look into that. So thank you, Alexis. And if it doesn't already exist, then I would be happy to develop one as well.
And just to follow up on Mike's question, Colin responded that he'd say roughly between 10 to 15K, depending on the fixture type, but that's a good starting range for all you folks at home. I think
sorry, that was just a question. Is that that's operating cost or is it upfront cost?
I took that was upfront cost. So I took Mike's question to be like, what would be the startup cost? And
okay,
it looked like roughly it's like 200 fixtures, I think, in order to get that area at 200 micromoles. So that's where I went, and it could go up or down depending on if you looked at a fixture, different fixture output, and a different number of associated fixtures that you would need, that at least kind of gives you a good idea of what it would take. And that's no small area, 10 by 100. That's, good starting like trial area for sure. Sometimes we see it on a per bench basis, but as far as tomato, I think an entire gutter length or house length would typically make the most sense.
Awesome. A lot of action going on in the chat right now. Trevor asked, are there programs or grants available to help with startup costs? And we got a response from Cindy. The KADB on-farm energy cost share program could possibly be used to upgrade existing lighting systems, HPS to LED, if an audit shows a significant energy savings. And there must be plenty of other funding opportunities. CAIP funding may be a possibility, depending on county level programs and cost of system. Since we're running out of time, I guess just a final question of, as a startup, like as growers are taking the plunge into creating their lighting plan, what's the first step? Do they call extension? Do they call a Colin type person at one of these lighting companies? Or what would you guys recommend as a kicking off point for folks?
Arundathi, you want to take that one first?
Sure. Yeah. Well, I would certainly encourage folks to reach out to extension as a first step. I think your county agents and campus extension staff are also happy to help folks talk through the motivations, particularly behind introducing lighting, so that you can feel confident that you're actually taking the right step. In general, I always encourage folks to start out small, because it's hard to predict what kind of business improvements to expect if you haven't actually tried it out a little bit on your own. So whatever materials folks have on their own, I think it's worthwhile to see, okay, if I really start boosting up my lighting in these colder months, how much is that really improving my crop based on the way that I manage it and based on the way that I manage my farm and where I am. And I think once you feel secure about the benefits that lighting is going to present you, then that's probably the moment to actually start consulting with technical service providers, lighting companies, designers, and actually understand what is it really going to cost to expand that feature out. Would you agree, Colin? Is that what people should bring you?
Well, I think the only thing I would say I would recommend differently would be to like do both at the same time, but be cautious of going forward in the lighting specification process, without like sniffing out a couple companies. I'm like, it would be disingenuous of me to say like, just talk to me. Like you want to feel safe and confident that you're exploring your options. But what I fear is if you go purely the extension route at first, you miss out on some of the commercial knowledge that's there. And I feel like we unfortunately are where there's a bit of a siloing, and I wish it weren't the case, but that way you kind of can learn everything you can at first, take that back, and then say, all right, who's providing the best, most accurate information on a commercial level, and then always feeding that back through your whatever consultative network you have, whether you have a crop consultant, whether you're talking to Arundathi and her group on a weekly basis. That way you just kind of can check all those boxes of making sure you're not getting led down a windy path to having too many lights, or buying lights when you actually couldn't benefit from having lights. There's cases that we would recommend not to install lights. We have to be honest about that, because we want to be around a long time, so we never kind of benefit from forcing the issue.
Awesome. I think we will wrap it up, but I just want to give you, Arundathi and Colin, a huge thank you for being with us today.